Let's move on to the next segment now. I would like to welcome Alan Pryor, Vice President of Simulia Worldwide Center of Excellence. Hi, Alan.
Hi, Samanth. Hi, everyone.
How are you doing?
I'm doing well.
Are you enjoying the conference so far?
I am. I think I'm going to use the word inspiring.
Inspiring.
Inspiring,
okay.
Particularly yesterday's general lecture with Bruce and Reza.
That was fantastic. There was lots and lots of technologies there. What did you learn from that session?
Two things struck me. Yeah. The first was the additive manufacturing, which I love. I think that link between the design and the manufacturing process that we've got so close in that app is wonderful. And the second thing is this idea of engineered materials. This idea that you can create a material for a specific purpose, I think that's really inspiring. Which brings me to our next speaker. So if you don't mind, sure. It gives me great pleasure to introduce our keynote lecturer for this afternoon. Silvestre Pino is a professor of mechanics of composites and EPSRC research fellow in the Department of Aeronautics at Imperial College London. Back in 2010, Silvestre was awarded the Albert Cardon Medal by the European Society for Composite Materials, which is awarded to the youngest or the best young researcher in the composites technology area in Europe. And I've known Silvestre for nearly 10 years. And during that time, the thing that's impressed me the most is the imagination and the innovation in the work that he does and the work that he does with his team. So I'm sure this afternoon's lecture is going to be extremely interesting. I think you're going to love it. So on that, please join me in welcoming Professor Silvestre Pino to the stage.
Thank you very much, Alan, for this very kind introduction. I think I must start by repeating the words that Alan said about inspiration. I have found this conference so far very inspiring, particularly on what concerns the vision that it projects for the future. So not just technologies for now, but this coherent view of where we are going as a simulation community. So having said that, my talk is about simulation methods and also, coincidentally, a new paradigm for the future, which has to do with designing new materials. So this is the outline for my talk. I will focus on 3 different themes that have to do with the numerical methods that I'm currently implementing in Abaqus together with my team. And finally, a 4th topic, which is related but slightly different, using simulation methods to actually design materials. So I'll start with this first topic, which is a molecular dynamics finite element method that we have implemented inside Abaqus. So this is work that was carried out to a very large extent by a former PhD student of mine, Andre Wilms, who is sitting currently somewhere in this audience and was funded by the Fonds National de la Recherche of Luxembourg. So the motivation for this work was the discovery of graphene in Manchester now already quite a few years ago, and the prospect of using graphene to build composite materials, to build electronics and sensors, and also to build membranes. And in this type of applications, if we want to realize this, we need to be able to do simulation across several physics and also across several length scales. And that brings challenges. If you look at the current simulation map, and this is a version of a graph that you will have seen before in this conference, we have different solution technologies at different length and time scales. At very large length and time scales, we have finite element method, for instance. At much smaller scales, we'll have molecular dynamics. If you want to have a multiscale simulation, you will need to somehow be able to transfer information from one to the other through an iterative process, which is not always very computationally efficient. What you would like to aim at is at a framework where we have a universal numerical platform with compatible solvers that allow you to do seamless simulation across scales. So it's in this context that we've tried to implement a molecular dynamics simulation tool inside Abaqus that can be used, for instance, together with continuum mechanics. So that covers the motivation for this work, and in this molecular dynamics talk, I will show you some details about the model itself, and I will show you some applications before concluding. So if I move to the model, if you consider an atomistic domain, so these are several atoms modeled one by one, you may be interested in applying forces to this atomistic domain, you may be interested in injecting charge to it, or to superposing an electric field. In each case, you want to solve this to find the state of your system, and the state will be defined by the displacement of the atoms, their charge, and their induced dipole. So what we want now is to formulate equations that represent all of these. Now, we started with Hamilton's principle, and we worked out all of the equations into a form that becomes exactly the same as in finite elements. So if I show you how this system of equations is formed, it's actually really simple. The key thing is to get a little bit away from the idea that elements represent a certain portion of space. So in this case, elements will bring parts of the physics into our problem. So if you think about inertia, for instance, we started by creating one-noded elements, getting their mass, and then for each atom in our structure, seeding that mass and assembling everything into our mass matrix. So at this stage, we have many elements, and we only have inertia in our system. The next step is to look at the force fields that you have in molecular dynamics. Force fields are typically additive, and you start, for instance, with some terms which involve only two atoms. We can represent that with two-noded elements, from which we obtain the Jacobian and the Hessian, so the stiffness and tangent stiffness matrices effectively, and we can mesh these everywhere. And then we have other terms of the force fields with three and more elements, and we do the same thing. We create three-noded elements, mesh them everywhere, and so on for all of the physics, all the mechanical part, and also all of the electrical part. At the end of this process, we have several superposed elements in space, and what they do is bring together all of the physics of molecular dynamics inside Abaqus. So this is the theory, and the way we've implemented this was in a very high-level way. We've implemented it in MATLAB in a way that we have the force field written analytically, and we get all the matrices, the Jacobians and the Hessians, calculated symbolically, the user element files in Fortran written automatically, and also the input file created automatically using some pattern recognition software to detect where the elements are. So this is my summary of the model. Let me show you now some applications. I'll start with a validation example. This is a carbon nanotube at 300 degrees Kelvin, and it's vibrating. And if we compare our solution in Abaqus, both with an implicit and an explicit solver, we get exactly the same solution as we get with LAMPS. So we are not creating an approximate version of molecular dynamics inside Abaqus. We've created actually an exact solution of what you can get in molecular dynamics, but inside Abaqus. So if we try to compare our solution with other results in the literature, for instance, carbon nanotube loaded in tension until it breaks, we get exactly the same solution as molecular dynamics for different types of defects in the nanotube and also for different chiralities. If we look at the failure process, so this is a carbon nanotube with a stone walls defect. Our simulation is the one that you can see in the center, and it's being loaded slowly. You'll see the failure appearing, and we get exactly the same failure pattern as you get with a pure molecular dynamics code. We can run our code inside Abaqus up to very large atomistic domains. For instance, in this graph, you can see simulations that we've done with a single desktop computer, so not even with a high-performance cluster, where you can get a linear scaling of computational time up to 1 million atoms. This is an example that we compared with an example we compared with literature, where we have a graphene sheet with charge injected, and we see the charge repelling itself. This is a case where we have a separation of charge inside a nanotube motivated by an electric field, and we can also inject charge and obtain mechanical strain as a result and simulate all of that inside Abaqus. In this case, we have a membrane which is at a finite temperature and vibrating. You have charge, and the charge distribution changes as a potassium ion approaches, so we can potentially use this as a sensor for the presence of that potassium ion. Now, because we are doing this in Abaqus, we have different types of solvers, and one thing we can do is, for instance, eigenvalue analysis. So we can get very easily buckling loads, buckling shapes, vibration frequencies, and vibration modes in a very efficient way, as you get in continuum mechanics. Now, the reason we are doing this is because we want to be able to simulate relatively large problems. And for this, one of the things we want to do is to be able to homogenize the properties of our material. Now, typically in continuum mechanics, when you want to obtain homogenized properties, you create a unit cell model and apply periodic boundary conditions at the sides of that unit cell model. With molecular dynamics, it's a bit more difficult because your physics is non-local. You have long-range interactions, so you cannot simply cut the boundary and apply something at the boundary. But we are able to work out the boundary conditions for this case, and if you look at these bars, what they show is different coefficients of the D matrix, which represents the homogenized bending properties, in this case, of a pillared graphene structure. So we can get homogenized properties, and the implication of that is that we can have this type of simulations as shown currently on the screen, in which part of our domain is modeled with molecular dynamics inside Abaqus, and part of it with continuum shell elements. And some of you will have seen this type of multiscale simulations before. The thing that is quite unique about this one is that we don't have two different solvers communicating with each other. We have one single solver, one single system of equations simulating two different physics at the same time in a seamless way. So if I summarize the conclusions of this part of the work, I've shown you a molecular dynamics finite element model which can do multiphysics, can do multiscale in a seamless way, can do bond failure, scales linearly up to millions of atoms, and can be run in implicit, explicit, and also for eigenvalue analysis. So if we think about this picture that I showed you before, I've added a green shade on the left because what this work represents is really trying to bring together molecular dynamics and finite element method into a common platform. For instance, with this platform, if you have an engineer that knows how to use Abaqus, he'll be able to do this type of simulations without learning or without having to master a second numerical simulation tool. So that was the first part of my presentation. I will now move a little bit up the scale and talk about the floating node method. The floating node method is a method that we've developed for simulating cracks in actual materials. So before I start, I'd like to just acknowledge the people that were involved in this work. Firstly, Boyang Chen, a PhD student of mine who graduated recently, and that was the first student on an exchange program with NUS in Singapore. Nelson Carvalho, a former PhD student of mine currently here in the US at NASA Langley, who implemented also some parts of what I will show you. And then Professor Tay in Singapore and Dr. Baez at Imperial College. So the motivation for this work is the simulation of composite structures. One thing which is very specific about composite structures is that if you want to design a composite structure until its breaking point, you have to be able to simulate not just the formation of the first cracks, but actually the formation and growth of many cracks that grow, they meet each other, they interact, they change direction, which we call kink, they kink into another direction, and it's only subsequently, after all these interactions happened, that you get the final failure of your components. And therefore, that poses an enormous challenge for simulation tools. So this is what we are trying to address with this. And there are, again, 4 parts to this section of my presentation. I'll show you first some of the theory behind this floating node method, then some applications, and then conclude. So starting with the theory, in finite elements, you have a global system of equations. This global system is made by the assembly of the contribution of many different elements. And what we do in the floating node method is that the contribution of each element is itself the assembly of the contribution of many sub-partitions, which are themselves the contribution of many sub-partitions. So what does that mean in practice? Suppose you have an element inside a mesh, so I'm just drawing here a schematic of a mesh and an element with the letter omega. This is our element. I'm drawing 4 circles at the corners. Those circles are meant to represent real nodes. So nodes are entities that have coordinates and that have degrees of freedom. So you can imagine those at the corner of your element. In addition to those real nodes, we have floating degrees of freedom. And these floating degrees of freedom is what I'm indicating there with triangles. So floating degrees of freedom don't have coordinates associated with them, but what they do have is a topological association either with the edges or with the inside of your elements. In a 3-dimensional setting, they can also be associated with surfaces of the elements. And what these floating node methods can do is that once you want to represent a crack inside your element, you can use them to effectively represent those cracks. So in those examples that you have at the bottom of the screen, from left to right, you can see a strong discontinuity, a crack, a weak discontinuity, so an interface, for instance, between 2 different materials, a cohesive crack, a T-shaped crack, or 2 intersecting cracks. And you can do that because you have floating degrees of freedom that you can associate to the relevant positions as you see fit. So that's the theory. Let's look at some applications. The first application that I want to show you is an application which is relatively simple but very difficult to simulate with existing techniques. That's the case of delamination, which is a crack that follows an interface, which migrates into a matrix crack, therefore changing direction, and then changes again direction into another interface, another delamination in a different plane. So I'll compare this against experimental data. This is an experimental setup that was developed at NASA. And what they've done here is to fix the bottom part of a composite specimen at both ends and then apply somewhere along the middle a vertical load upwards. And the position of this vertical load, which is characterized by distance L in the screen, is a variable distance. So you could do that at a certain distance or do it at a different one. And what happens when you apply that force is that the crack grows in a very peculiar way. So I have now some drawings that allow you to see that. So at the beginning, the diagram shows the initial crack that you have in your specimen before the crack starts growing. Then as you increase the load applied, the crack grows in the position in green as shown, in an interface between a 0-degree ply and a 90-degree ply. Then after it has grown for a certain amount of time, the crack changes direction and migrates through this 90-degree ply in a shape which is not a straight change, so you have a curvature there. And then thirdly, the crack continues in the different interface. So what James and his co-authors measured at NASA were the low displacement curves, the location for crack migration, and also the shape of the crack path. So all of those are things that we want to try to replicate numerically. So we've built a numerical model of this specimen, and because we have floating degrees of freedom, we can use them to simulate these 0, 90, and 0-degree plies where all the action happens, which means that inside our element we have information about the 3 different plies simultaneously, which we can use to define criteria for whether or not those cracks should propagate, as well as for then simulating the propagation of these cracks. So if you look at the first case they've done, you can see the low displacement curves on the screen. The experiments are in gray and the simulation in red. If we change the application of the load displacement curve, we get very similar load displacement curves, and in all cases, we get quite a good prediction of the maximum load. If we look at the position of the migration, here I'm plotting in the horizontal axis the 4 different cases that they've tested. In the vertical direction, the distance d at which the crack migrated from one plane to another. You can see the simulations in red and the experiments in black agree very well. If we look now at the shape of the migration, I'm superposing our predictions with an actual micrograph of that migrating crack, and you can see that we have a very similar shape. So that was two-dimensional and static. Now I'm going to show you an application or an extension that Nelson at NASA did for fatigue loading. This is a DCB specimen loaded in fatigue. So fatigue is something that I would assume most of you are familiar with. In case someone is not familiar with, if you load a certain piece of material until a load that should not lead to crack propagation, but you do it repetitively for thousands of cycles, then cracks can still grow in this way, which we call fatigue. So in this plot, I'm showing crack growth as a function of the number of cycles. In black, you have benchmark results. In green, you have the predictions that we got with the floating node method. And as you can see, they agree very well. So all of this is two-dimensional. And for these cases, there are other methods that have existed for some time that could do relatively similar things with more or greater, with less or more difficulty. But what I'm showing you now is applications in 3 dimensions in which the number of cracks that we are simulating makes it very difficult for any other methods to replicate. So the first case, relatively simple. It's an open hole tension specimen. Open hole because it has a hole in the middle. This is a rectangular specimen, and I say it's a 0-degree UD lamina because it's made of carbon epoxy material in which the fibers are in the horizontal direction. So we are loading these horizontally, and as we do that, what you will have is splits in the matrix parallel to the fiber. In the drawing on the top, I will show you the matrix splits being formed. On the bottom, the stress in this open hole tension specimen. As you can see, the mesh has been very carefully done in a way that is not structured so that we are not guiding the direction of the cracks in any possible way. And this is final collapse with many cracks in this 0-degree lamina. So now I'm going to show you another example in which the fibers are at 30 degrees. So that will affect the direction in which the cracks can grow. And it will also affect the number of cracks that you get in your specimen. In this case, as soon as these 2 cracks got completely formed, the stress field becomes uniform and nil because you cannot transfer any more load between the left and right sides. So now let's go to something slightly more complicated. This is a 0-90-degree specimen. So now you have 2 plies, one in which the fibers are at 0 degrees, horizontal direction, and one in which the fibers are at 90 degrees in the vertical direction, and they are bonded together. The cracks, you can see them in the top picture, and the status of the bonding between the 2 plies in the bottom picture. So black is perfectly bonded, and it will change color as it debonds. So you can start seeing several cracks starting to be formed. And at this moment, we have tens of them. Soon we'll have hundreds. And this is possibly, if some of you have been modeling fracture with Abaqus, this is probably the simulation you've seen so far with the greatest number of cracks in one single model. So at this moment, we have several hundreds of cracks simulated one by one in this specimen, and the simulation is still going until we get breaking of the fibers. Now, if this is the simulation you've seen with the greatest number of fibers, it will not remain so for very long, because in this specimen now, we have fibers not only at 0 and 90-degree directions, but also at plus and minus 45s. So now we have 3 different interfaces between the plies in the different directions. And the number of cracks that we simulate in this case is actually really, really large. You can see many cracks happening in all of these plies and the delamination between the plies growing progressively. So these were the applications with the floating node method that I wanted to show you. And if we now conclude, what we get with this method is an accurate description of kinking cracks just because of the way we treat our floating degrees of freedom. And this can be used for static failure, for fatigue failure, and it can represent very complex three-dimensional crack networks. So that completes the second part of my talk. I'll move now to the third part, which continues to grow up in length scale. So I started in molecular dynamics. Now I'm going to talk to you about a mesh superposition technique that we've developed to try to be able to predict damage at microscopic scales while simulating components which can be several meters in size. So this is the third part of my talk and the last numerical method development that I'll show you. So this was mostly done by a PhD student of mine who graduated just about 2 or 3 months ago, Luigi Gigliotti. So the motivation is this type of example. So we are not trying to design this specific helicopter, but I will use this example of this helicopter repeatedly through this part of my talk. So suppose you have a helicopter with blades, and the blades are made of a carbon-reinforced plastic, which is a sandwich structure. So you have carbon fiber composite skins, and you have a foam core. And to make it a little bit more difficult, we have a regular pattern of carbon-reinforced pins bridging the two sides of the sandwich structure together. So this is a very complex microstructure. If you try to simulate failure of the pins, you need to be able to have a space resolution which reaches fractions of millimeter, but you want to be able to do that while modeling things that can be quite large, so several meters in size. So our simulation will look something like this. Imagine you want to simulate an impact at a very specific location. I'll talk to you about 2 different challenges in doing that. One of them is how you link these different scales in your model. Imagine a central scale in which you have 3-dimensional elements and a second scale in which you have homogenized shell properties. And the second challenge is to efficiently calculate homogenized properties. So in this section of my talk, I'll have 4 parts again. I'll talk a little bit about how to do this mesh superposition technique, how to obtain homogenized properties. I'll return to this example with the helicopter and show you how we could potentially use these techniques to design this blade, and finally conclude. So starting with the mesh superposition technique, imagine you have 2 different realities or 2 different meshes. What you typically do to bring them together is to have a common boundary between them. That's definitely not what we are doing. What we have is a blending of one mesh into the other with a handshake region or a mesh superposition region in between them. So this is how we can see things in a continuum world. In a discretized world, what we have is 2 different meshes, so the mesh in green and the mesh in blue, together with a region in between where one mesh progressively disappears and the other one progressively appears, so that we have this nice result of one mesh blending into the other. So how do we get the blending elements to occur? Well, when we define the stiffness matrix and their mass matrix, we have these functions psi that you can see there in red, which are just weight functions that verify partition of unity so that we get the correct physics, and they can be defined with a level set method so that we get the blending region in space done efficiently. So this is the theory. Let's look at an application of that, a low velocity impact on a composite plate. This is a plate which has 3 plies, a 0 degree, 90, and 0. It was tested in 2008 by Emerich et al. And what they've observed was that the first thing to fail when there was an impact in the center was the bottom ply, where you'd have a crack shown in green. Then you'd have delamination between the 0 degree bottom ply and the 90 degree middle ply. And this delamination will have this form, this shape shown in red of a peanut. And this is what we want to simulate. Now, this problem is doubly symmetric, so if you want to do a finite element model of these, you can exploit the symmetry and model only a quarter of it. So we've done not one, but 3 such finite element models. One in which we modeled everything in 3 dimensions. The objective of this model is to obtain a reference numerical solution. We've done one model in which we have a sudden transition between part of the model in 3D and part of the model with shell elements. And we've done a third model with our mesh superposition technique. So if I show you first the results with the fully local model, this is the delamination growing. You can see it's getting that peanut shape. And if you compare that against the experiments I had shown you before, you can see that they match pretty well. So it's a good detailed numerical model. If I show you now just the 3-dimensional part, so the local part of the model with a sudden transition, you can see that as the delamination grows, you get some damage at the intersection between the refined model and the shell model. And this is to be expected because you have some stress concentrations there. Now, if I show you the same thing for the mesh superposition technique model, now you have exactly the same size of the local mesh, so absolutely no difference, but you obtain the same result as in the fully local model. Now, some of you could argue if we had a local model slightly bigger, the sudden transition model would still work. Now, of course, this would come at a computational cost. So the proper thing to do in terms of trying to measure the merit of this mesh superposition technique is to compare the computational cost of the most efficient mesh superposition model with the computational cost of the most efficient sudden transition model. And if we compare that, what we get is a benefit in terms of CPU time between something like 20% and something like 50%, depending on whether we only use an explicit solver or whether we use partly an explicit solver where we have damage and an implicit solver where we don't have damage. So that's a very significant improvement in computational time. So that's what I want to tell you about mesh superposition. Now, very briefly, I'll talk to you about homogenization. So what we want to do here is to apply in-plane loads to a unit cell, so stretching and shearing, and obtain the homogenized properties that allow us to apply in-plane loads to a homogenized shell element, and also to apply bending and twisting. And in this way, we can have a full ABD matrix, for those of you who know shell theory, or in general, we can simulate a homogenized shell response of this structure. So this is something that has existed for some time, so there's nothing new in calculating homogenized shell properties with unit cells. But what we've done was to use the symmetries in the unit cells so that instead of actually simulating an entire unit cell, we simulate, in this case, only a quarter of it by exploiting the symmetries that we have inside. And with that, we can, quite surprisingly, reduce the computational cost very considerably to 1/10 of what we would otherwise have. So that's the only thing that I wanted to say about homogenization. And now I want to return to this simulation of a large composite structure using these techniques. So this was our helicopter. Remember, we have failure of pins close to the impact region, and we are trying to simulate a very large sandwich structure. So this is our model. You can see on top the implicit part of it, which is most of the model, and on the bottom a refined region which is modeled in explicit. Now I'll show you in more detail this refined region in explicit. It has a central part where, in addition to what you can see on the screen, there is also the foam. I'm not showing you the foam so that you can see the pins inside. And in this region, we are simulating the crushing of the core, the debonding between the core and the face sheets, and also the delamination between the different carbon epoxy plies on the face sheet, and crucially also the failure of the composite pins that bring the face sheets together. Then we have a mesh superposition transition to a second region where now we are only modeled the bonding and delamination. The reason for that is that this type of failure, the bonding and delamination, extends on a length scale which is bigger than that where you have crushing of the core and where you have failure of the pins. And then we have another transition now between a solid mesh and a shell mesh, again done with superposition. So if you put all of this together in the simulation of this blade, then what we get is this simulation here. Let me see if the videos play. The videos are refusing to play. They played 5 minutes ago. Let me try again. Yes, they play now. So you can see on the top two models at different time scales, implicit and explicit. In the center, different length scale models and different types of damage simulated at the bottom. All of these in a single process, so not with different solvers having to communicate with each other, but as solving one single system of equations, so in a completely seamless way. Okay, and that finishes this application. So if I conclude this mesh superposition part of my talk, what I've showed is a process which allows you to have smaller and faster refined regions and therefore achieve a significant time efficiency. So that was the third part of my talk, and it was the last one in which I talked about the development of numerical methods. The fourth part is going to be conceptually very different. When we develop numerical methods, of course, we partially do it for the pleasure of it, but to a great extent, we must do it for their potential application. So what I'm going to show now is something which is very much in tune with many things that were referred to during this conference in the last 1.5 days. So if you want to, for the sake of argument, design an aircraft, so suppose you are this person in black and you want to design this aircraft on top. Traditionally, you would think of this problem as a problem of designing a composite structure using existing libraries of possible materials. And what I suggested a few years ago when I applied for resources to fund the work that I'm about to show you was that in the future we should be thinking about not designing the structure with existing materials, but point by point designing together with the structure the underlying material. And if you've been attending the talks in this conference over the last 1.5 days, you will have heard many people voicing very similar ideas. And I could not help yesterday evening not including this quote in my presentation that Max, the CEO from Biovia, made yesterday. Engineered materials create materials for purpose, not purpose for materials. That's exactly the same sentiment or the same vision that I am trying to express here. So what I proposed a couple of years ago was that we should try to do the following. Suppose you are designing this aircraft. For the sake of argument, say that you are designing a point on the leading edge of the aircraft. In that leading edge, you must try to identify what are your requirements or what are the driving design factors. And suppose, for the sake of argument, that this is damage tolerance. And this is what this picture is meant to represent, a crack propagating. So how much energy does the material dissipate as you propagate damage through it? That's what matters if you have a bird hitting that leading edge. Then you would think of a concept for a microstructure that could be suitable for that type of requirement. So if you are talking about resisting cracks propagating, you might want to have fibers in a direction perpendicular to that crack, organized in such a way that they have to pull out from both sides of the fracture surface, therefore dissipating a large amount of energy as they do so. And then you'll use numerical methods, such as the ones that I've shown or others, to actually design the details of that microstructure. Then using additive manufacturing, for instance, that Alan mentioned before, you could create prototypes for those materials, verify experimentally whether they work, and then hopefully finally create a product that you can put in the market. So in the next 3 minutes that I still have, I want to show you what we've done with this type of ideas in the last couple of years, and focusing on the actual generation of the materials, not just the numerical methods. But if you look at the title of this part of the talk, engineered fracture surfaces, so that relates very much to engineered materials, but we are looking specifically at engineering the fracture surface that they exhibit. So this all started by looking at these fracture surfaces in fiber-reinforced composites, where we already have naturally occurring different scales of pullouts which dissipate energy. We've built over the years models that can represent how those scales form and how they dissipate energy. So we had a good understanding of that, but they were formed naturally, not on purpose. And this is very different from what happens in nature. If you look at nature, say bone or wood, for instance, you have a microstructure with different scales that have evolved to be there, because when you try to break wood or when you try to break a bone, then that creates a very tortuous crack paths which dissipate a lot of energy. So we try to borrow those ideas, and I'm going to show you some of the materials we've created. So this slide has a single purpose, which is to help you understand the slides that follow. So this is called a compact tension specimen. What we do is we take a specimen with a central crack and we open it and we break it apart. If you look at the zoom you can see a crack there growing from your left to your right. If you look at the bottom half of that zoom and you look from above, imagining the top half removed, this is what you'll see in these next images. So this is a standard unmodified carbon fiber composite with some 0-degree plies. It's the fibers that you see sticking out from the fracture surface, and some 90-degree plies where the fibers are running along the fracture surface. So if you look at this image, the people who know carbon fiber composites will look at this and think this is a very brittle behavior because the pull-out of the fibers is very small. So if you look at that scale, those 0.3 millimeters, you can see that the fibers, which have about 5 micrometers in diameter, they have a pull-out which is really just micrometers. So this is very brittle. So by comparison, now using exactly the same scale, this is the type of materials we were able to design first and produce next. So these are materials in which the fracture surface is the result of the microstructure that we engineered into the material, and now you have much larger pullouts that dissipate more energy. We can do this with one scale. With 2 scales, we can create at this stage whatever patterns we want to create, and we can even, if we were so inclined, create a microstructure such that when you break the material, it spells Simulia or Dassault Systèmes on it. The last microstructure we created is this one. We called it a shark teeth microstructure because it has these teeth that look like shark teeth. And about this microstructure, I'll show you some numerical data. On the left, you can see the load versus displacement response. In black, the baseline material with a peak load of 1 kilonewton. By modifying the microstructure locally, so exactly the same constituent properties, we just modified the microstructure, we got a 66% increase in notch strength. That's not a minor increase, 66. We went from a discontinuous crack jump propagation during failure to a very smooth propagation. And if you look at the right-hand side, we have a 5.6-fold increase in energy dissipated during fracture. So if you imagine that we were designing that leading edge of that aircraft, that means we could deal with a bird 5.6 times as heavy. So this fits into this vision, which is not just about damage tolerance, but about identifying requirements and designing the material point by point to address that. And this is the end of the 4th part of my talk and of my talk as a whole. Thank you very much for your attention.
Thank you very much, Dr. Pino. Thank you, Dr. Pino. Fascinating presentation. What you presented is a perfect complement to what was being talked about yesterday in the keynote presentations. But most of all, I appreciate that the presentation style that you had was beautiful. Even I could understand what multiscale modeling is all about. Thank you very much.